Math 2414, other convergence test, another comparison test example. Actually, this should probably be titled something different because it's going to be more than one example. So we'll say more comparison test examples. There we go. All right. So on the screen currently, you see the comparison test from the previous video where we have two series whose terms are positive, and one set of terms is always less than or equal to the other set of terms, or at least eventually. If the larger series converges, then the smaller one converges as well. But if the smaller series diverges, then the larger series diverges as well. The whole floor ceiling analogy. If the floor doesn't go up to infinity, then neither can, excuse me, if the ceiling doesn't go to infinity, then neither can the floor. And if the ceiling goes to infinity, it forces the floor to go to infinity as well. So let's take a look at three examples. Determine if the following series converge or diverge. I found it interesting that the word series is both singular and plural at the same time. In this case, it's plural because there are three series we're going to look at. You're looking at the first one right now. The sum from n equals 1 to infinity of 2 to the n over 5n cubed plus 4n. Now, if you're going to do a comparison test, then you need to ask yourself, what series would be easier to work with that kind of looks like this one? One trick is to consider just taking the leading term in a polynomial. Like when we did this isn't a polynomial. Like when we did this one in the previous video, we got rid of the +1 and they gave us something we knew about. So we're going to do the same thing here. But you have to be careful to ask yourself what happens when I lose terms. For example, on this one, let's say that we just took the leading term on the top and on the bottom. It's convenient when you have a monomial on top of another, as you'll see in just a second. But if we compare this series, we have a constant factor of 2/5 that we can pull out. And n over n cubed would reduce to 1 over n squared. So I already know what this does. I know exactly what this does. This is a p-series where p is equal to 2. And if you recall how we summarize p-series, when the p is bigger than 1, greater than 1, we get convergence. So we already know that this series converges. But in order to draw a conclusion, we have to hope that the green series is the ceiling, because if the floor is less than that, then the ceiling won't let it blow up to infinity. If the green one happens to be the floor, then it won't tell us anything about the ceiling, because the floor can settle down, the ceiling can keep going up. But we have to establish which of these is the lesser of the two series, and I'm hoping it's the original. So we need to compare the individual terms. And it's worth noting that these terms are all positive, so we get the bounded below by 0, if you will, for each term. And here we're just going to use some logic in terms of, that's potential spam, not going to answer that, in terms of larger numerators and denominators. This is usually how you determine which fraction is smaller and larger, by analyzing, did you just make something larger or smaller in the problem? For example, when we went from here to here, keeping in mind that all these terms are positive because n starts at 1, which of those circle things is larger? The answer is the one on the left, because this plus 4n is a positive number, and if we add it to this, we get a larger result than if we didn't add it to it. So we know that the fraction on the left has the larger denominator, and as a consequence, that means that the fraction on the right is the smaller of the two fractions. Give this a draw, cooperate. And again, since n is positive and there's no negatives in sight, we get the greater than or equal to 0. So if we were to look at this at the series level, add up all these terms, and by the way, this relationship that the first term is less than or equal to the second is not eventually, it's always in this case. But if we were to Say, all right, we know that one term's less than the other, so the first sum is less than the second sum. And we've already determined that this sum, that was supposed to be in green, this sum converges. So we've got a ceiling, larger sum, above the floor, the smaller original sum, and the ceiling is not going to infinity. So the floor, as it rises, can't go any larger than the ceiling. Therefore, the original sum, 2n over 5n cubed plus 4n, converges by comparison. We found a larger series by removing a term in the denominator that converged. Everything was positive, therefore converges by comparison. Let's take a look at another. The sum from n equals 1 to infinity of the natural log of n over n. Now, if you pay attention, take notes, and have already watched some previous videos, you may recognize this series as one of the examples we did from the integral test. If you don't remember how it ended, or if you didn't watch that video, I'm not going to tell you how it ended, but the purpose of this example is to show you that when you are choosing a test, check a series for comparison, you have more than one option. Not all tests will work at all times, but sometimes you have choices. So let's try this by comparison. Now, what series kind of looks like this that we know something about? What if, this is the hardest part about comparison test, picking the series to compare it to. What if the numerator wasn't the natural log of n, but just a 1? I know what this series does. This series diverges. It's the harmonic series. It's also a divergent p series with p equal to 1, but you need to recognize a harmonic series from a mile away. This diverges. Now, I haven't set up the comparison yet between which one is larger than the other, but knowing that this diverges, I'm hoping that the second series is the floor, because if the floor goes to infinity, it pushes the ceiling up to infinity as well. If the second series was the ceiling, and it went up to infinity, you have no idea what this floor is doing. So I'm hoping that when it's all said and done, we're showing that the original series is bigger than the series that we know diverges. So how are we going to compare this? So we need to compare individual terms versus this. Now, because these have the same denominators, the dominance here, who's larger and who's smaller, hinges solely on the numerators. So let's think about the graph of natural log of x. And this is the graph that you just flat out should know. Vertical asymptote on the y-axis, x-intercept of 1 starts low from the asymptote, crosses the x-intercept, and then makes a very slow journey to positive infinity. If we're comparing the natural log of n versus 1, you can see from this graph that once you hit the number 1, this graph is above the x-axis, meaning that the natural log of x is greater than or equal to 1 when x is greater than or equal to 1. That means in our comparison over here on the left, we can say that the natural log of n is greater than or equal to 1. Excuse me. We're comparing to 1, not to 0, so I'm not ready to make any conclusions yet. Well, if 1 was over here, excuse me, if 1 was over here on the y-axis, then it should be pretty obvious that there is some number n so that the graph is higher than 1 from that point forward. Where is that number? Well, that's the same as solving natural log of x is equal to 1, but we did that in a previous video. That number was e. So at the number e, about 2.72, or if you want to be more accurate, 2.718281828459045 and more. But at the number e, the natural log is equal to 1. And because the natural log is an increasing function, that means that if x is greater than e, then the natural log of x is greater than 1. So we can confidently go back over here and replace the versus with greater than or equal to, if I can get it to draw, and stick on the word eventually. Natural log of n isn't always greater than 1, But once you go past the number e, in other words, once you hit 3, he's over here somewhere. Once you hit 3, then yeah, it's always going to be greater than 1. Natural log of the n is always going to be greater than 1. So we've got this, and we've got this, and we've got a divergent floor. It is worth noting, and I'm going to have to move my picture for this, it is worth noting that everything here is greater than or equal to 0, eventually. Well, we're starting at 1, so we're not less than 0 there, but this entire double inequality that the original sum is greater than or equal to, and this is getting really messy. Let me clean this up a little bit. That helped. The original sum is greater than or equal to the sum from, actually, from a technical perspective, we can't even say that. But what we can say is once we cross 3, this is all good. So even though we're comparing the sum from 1 to infinity, I'm going to change these from 3 to infinity. And this is just a little CYA move. If you don't know what CYA means, then go look it up. But once we cross 3, natural log is greater than 1, which means the first sum is bigger than the second sum, but everything's positive, so we have that. And so that means that we have a ceiling in the original sum. We have a floor, the one in the pink box. The floor goes to infinity, and it pushes the larger sum to infinity as well. So after all that, we can finally say, if I can get all this. Ooh, that's nice. Select and delete. All right, so after all that, we can finally say without any hesitation that original series diverges by comparison. I guess you don't have to capitalize the word comparison there. And you might be thinking, but you changed it from 1 to 3, and you're right. This series, draw please. This series, in green, nothing's cooperating. This series diverges. And if we add on 2 more terms, it's not going to change the convergence or divergence nature of it. Convergence or divergence does not happen at the first few finite number of terms. It's determined by the infinite end of the series, so we still have that infinite end. All right, so, but by the way, this was the same conclusion we drew with the integral test, that the improper integral diverged, therefore the series diverged. All right, let's take a look at one more. And if you watched the previous video, you might recognize this one as the one I started and abandoned because it wasn't the one that I wanted. But the purpose of this example is to fail so that we can motivate another technique. All right. So again, the trick for comparison often, especially in multi-term numerators or denominators, is to lose a term to create a series that we know something about. So if we compare this, sum of n equals 1 to infinity, 1 over 2 to the n, we already know that this converges. It's a geometric series, we'll just say GO, r equal to 1/2. So we want this one to be the ceiling and the other one to be the floor. So we want the one we just wrote to be bigger than the one we're looking at. If we have a convergent ceiling, excuse me, the floor can't go past that. But look at what we did when we removed the 1. When we remove the 1 and turn the denominator from this, when we remove the 1 and turn the denominator from this to this, we made the denominator larger. Or vice versa, if we start with 2 to the n and subtract 1 from it, the -1 causes that result to get smaller. The fraction on the left has the smaller denominator. They have the same numerators, which means the fraction on the left is the larger of the 2 fractions. Everything is non-negative, so we can say greater than or equal to 0. But we have the backwards of what we need. Our first series is the ceiling because it's the larger of the 2. Our second series is the floor. The floor does not go to infinity, but that doesn't mean anything about what the ceiling can and cannot do. So what's the conclusion here? The comparison test is inconclusive. That case. So the comparison test won't always get the job done. It's because it only works 2 out of 4 times. It works when you have a convergent ceiling, which means the floor can't go up to infinity, so it has to converge, or a divergent floor, which pushes the ceiling up to infinity, making the other series diverge. But if you have a divergent ceiling, in other words, the larger sum diverges, or a convergent floor, which we had here, you can draw no conclusions, folks. All right, so what do we do? Well, we resort to a new test, which I will show you in the next video. In fact, we'll use that test to determine convergence on this one. But before we do, I just want to appeal to your intuition. The series without the -1. Series without the -1, we know diverges. Excuse me. We know converges. That series is almost the same as the other one. It's a little bit larger. We took one away from the denominators. But what does your intuition tell you? Does your intuition tell you that, well, this has a larger denominator, therefore smaller denominator, therefore larger fractions, therefore it's probably going to diverge? Or does your instincts tell you, well, these are almost the same, just the -1. And trust me, when the n gets large, that -1 is almost insignificant. Like when n equals 3, our denominators are 7 up front and 8 in the back. So 1/7 versus 1/8. Think about cutting a pizza into 7 slices versus 8. One slice is clearly larger than another. But if the n were 10, then the denominator on the left would be 1023. The denominator on the right would be 1024. If you cut a pizza into 1023 slices and another one into 1024 slices, those slices are so similar, you probably can't even tell that they're different. My instincts say that the first series probably converges. But we can't run an instinct. But what we can do is use another test that's like the comparison test, but a little bit different. Check out the next video to see it.